Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing on visual saliency, and today we will continue this discussion. In the last lecture, we discussed how there could be some computational models for computing the salient regions of an image, where a viewer concentrates more upon those regions to understand and see. And we also talked about that finally that there is a need for validating those models and there is a need for capturing the ground truth. So today let us once again start our discussions on the validation of models. So as I mentioned that there are two methods for obtaining this ground truth data. So one of these approach is feedback from viewers, and the other approach is using a eye tracker, where you track the salient, track the points where a viewer is looking at, and finally analyze those regions to identify the regions of saliency. And again, all these things, whether it is feedback, that means the viewer is suggesting which are the regions salient, or whether an objective way of capturing viewers' viewing locations and then analyzing for computing those salient regions from that sequence, for analyzing those gaze sequence. But finally, we require to have some aggregations of those data from different viewers, from different perspectives, so that average viewer's response could be captured in the ground truth. So this is one kind of issue with respect to validation. There is another issue here also, that suppose you have this ground truth data and you have computed the saliency map, then how do you evaluate the saliency map with respect to the ground truth? That means we require different kinds of metrics, performance metrics for judging the performance of a technique. So here I will discuss about some of those measures which are commonly used in the literature. Now let us consider that we have the ground truth data which is shown here, which is represented as a function of points, pixels in the image, and similarly the saliency map is also a function of the pixel points. At every pixel you have a saliency value, and especially we also consider that from the ground truth data we identify the regions of saliency, which means that ground truth may provide some kind of degree of reference saliency at any point, but we can binarize them. We can provide certain kind of threshold beyond which we declare that pixel belongs to a salient region, otherwise in a non-salient region. So let us consider the region of salient points in the ground truth that has been identified, and that set is given by RS, and region of non-salient points in the ground truth that is denoted by RNS. So these are the few things which we require definitions to define different kinds of metrics. So first I will talk about this average discrimination ratio. So in this case we consider averages of saliency value, saliency map, what is computed in the salient region and also in the non-salient region. So now we find out that what is the proportion of those values, because these are all saliency values. So naturally saliency values in non-salient region should be small, so average should be low. On the other hand, saliency value in the salient region should be high. You note that when we declare a region, we have put a threshold value, so that suppose gxy is less than some value, some threshold value, saliency threshold value th, then we say that xy belongs to RS. else it is not less than, it is greater than threshold, then we say xy belongs to Rs, else xy belongs to Rns. So, in this way we have now identified those regions. But when I am summing up the saliency values within Rs, it is expected to be, the average value, it is expected to be quite high compared to those average values of the non-salient regions. Now, this is of course with respect to ground truth I mentioned, but what happened in the saliency map? So, saliency map also it is expected that no, in the salient regions it should be high and non-salient regions it should be low, and based on that we define a metric which is a ratio of the average salience in the salient region of the predicted map or saliency map with respect to the sum total of two averages of salient and non-salient regions in the same predicted map. So, you can see that here numerator is that average in the salient region, that saliency map values, and in the denominator you have sum of averages for both salient and non-salient. We call it average discrimination ratio, that higher the value the better is the computation, better is the discrimination power of the saliency map. So, that is why this is one kind of measure. There are also other measures. So, one measure I have mentioned here, shown here as Kullback-Leibler distance, which we know already. It is a measure distance between two probability distributions. Now, we consider, say, saliency can be also related to the probability of a pixel for being salient. So, we can always normalize the values, and by normalizing the values, that means you just the sum of saliences, you normalize the value by the sum of salience at every point. So, that would give you the probability of the saliency value at that point. So, this is called this is the Kullback. This is the probability value. So, if you get the probability distribution here, so that probability distribution will be two distributions. One is for the saliency map, so which is this Px is the probability distribution of the saliency map. So, we can define, I have shown it in one dimension, we can also mention that it is basically a probability of a pixel. So, xy. So, these are, consider they are all pixel locations. So, this is the total image. So, this could be defined as, say, m xy divided by sum of mxy, or if I consider that the max, we can normalize with respect to max also. Since it is probability distribution, so it has to be sum of mxi. Since it is probability distribution over x, it has to be sum of mxi. It is not that individual pixels. So if I consider this information, this is the distribution. Similarly, we define the hxy, which means once again this is xy. Again, with respect to ground truth we refer. You note these are double sum because there are two. So, this is the distribution, then it becomes sum of probabilities over the space is 1. So, the Kullback-Leibler distance is finding out the difference between these two distributions. So, higher the difference, we expect this difference should be small in this case. So, that is the idea. Then the other measure, which is correlation coefficient, very standard statistical measure. Once again, we can consider this is a distribution, so we can define its covariance between two variables, two random variable g and m, and similarly we can define the standard deviation of the random variable g, which is the ground truth, and m, which is the saliency map, and then correlation coefficient can be defined in this way. So, this is a covariance. I have just used simple notation g and m to denote the respective variables over space, and these are the standard deviations. We know these are the standard deviations. So, standard definition of the correlation coefficient, Pearson's correlation coefficient, and we know that the value ranges from -1 to 1. Now, we would like to have high correlation coefficient, positive correlation coefficients for a good model. Besides these three, you can consider also detection of salient pixel as a classification problem, whether a pixel is salient or not, and the ground truth, what the ground truth gives, that gives you that classification of every pixels, the true classification of every pixels. So now, with respect to that, you can define once again like a classifier. We can define its precision, you can define its recall or sensitivity, and standard definition of the precision, like here it is. This should be true positive and predicted positive. So true positives are the positive of the salient point which is in the map computed, and also it is in the ground truth. So that is the case of a true positive. And similarly, which is non-salient in the ground truth, if that pixel is also declared non-salient, that is called true negative. So the first thing would be true positive divided by predicted positive, which means that number of true positive that is detected and total number of predicted positives what is obtained, it is called precision. Similarly, if you have number of true positives what is being detected and actual positives, that means some of them are not detected. So that is called recall. And the sensitivity is that number of true negative. So it is also, the recall is also called true positive rate. And sensitivity is, it is not sensitivity, it is specificity. It is number of true negatives divided by actual negatives. So this is called specificity. Actually, recall is also called sensitivity. There is a term. These are the common technical term which is used for classifier. Recall is sensitivity. So all these values should be high. All these values should be high. It should be near 1. If I say close to 1, and the combined performance denote the corresponding classifier's performance. Now, it is not only a single value isolated, you should look at it. We have to look at all these values in combinations. So sometimes in some classifier precision could be high, recall could be low, or the vice versa. But we would like to get a classifier where all these values are in a reasonable range. Anyway, so these are different kinds of evaluation metrics. Those could be also used for judging the computational model to compute the saliency map. Now, I will discuss some of the methodologies for obtaining this ground truth, since we are discussing about this validation of the models, and in particular, I will give a typical example of one methodology that we have developed in 2009-10, in that year. So, what we do here, it's a subjective feedback, which means we have designed an experiment where images are shown to the display devices, and later on those images are again withdrawn, and only the blank screen is there. Then the viewers are asked to identify the regions of saliency from their memory, from their short-term memory. They have to basically mark those regions which they feel they have seen. So that is the salient. In this way, you are obtaining the saliency. But before that, what we would like to see also that about the nature of the viewer, because it's a psychology of a viewer is also involved. So what we see that how much the viewer is also capable of giving proper answer. So there is a technique we developed that is called hand-eye coordination technique. In this case, we test the viewer's ability to follow up the respective stimulus. So what we do, say you consider a computer screen, say it's a blank screen, and viewer is asked to identify certain point which has been illuminated, some spot which has been. So this will be illuminated and it will be withdrawn, and then viewer will be asked to highlight those points. So the deviation, so the actual point, so this is controlled, is also known by the system, and the recorded viewer's response is recorded. It is noted that what is the deviation of the distance from this point. So if a viewer can provide the feedback within certain range, so you take the average error. So if the average error lies within certain interval, then we select that viewer. So it is it's a through the experiments on different viewers, this average and the standard deviations are fixed, and then based on that, a viewer finally during the recording of data, first viewer goes through this test, and then that viewer is selected. Actually, anyway the viewers go through this test, it is to acclimatize the viewer in this scenario. So this is what is we call this stage as hand-eye coordination stage. First the viewer goes through it, and then viewer participates in identifying the salient regions after viewing the image. So what we do after that, the volunteer is shown an image for 15 milliseconds only. So these times etc. they are set by consulting the experts in that domain, and the respective the parameters of our psychovisual systems or responses, consulting them, these are set here, because understand it's a bottom up process. So we would like to keep it within that limit of the time interval. Then it has the less role for the top down component of attention. That's what I was trying to impress upon. And it cannot perceive changes in the scene staying less than 100 milliseconds. So that you should note here. So a background mask adaptive to the input image follows. So once an image is displayed, then a background mask after marking, then a background mask is followed, and then after that a new image is displayed. And then the volunteer is masked to mark at the center of salient locations, and 100 images, like 65 volunteers, 20 images per volunteer. So in this way we have captured the data, and this data is available in our website. You can see, and we call this data as IIT KGP visual saliency data, and it is available in my website. You can download this data for your experiments. One typical example of this data, you can see, of course there are many limitations, but this is a very simple way of capturing. That's what I would like to suggest here. So you can see that when a viewer has seen the image, then viewer has identified, say, these are the regions, and it is the average response finally after taking, say, 50 viewers response for the same image. Then we aggregate them and we giving the weights. Finally we identify those points which are most salient. So these are the points. You can see that there are two salient regions and which have been marked here. So one of the thing in this method bottleneck is that it does not give you a region, it tries to give you some points of most salient points. The center points are okay, but no, the spread of saliency map is not very clearly obtained in this ground truth. So we have tried to modify using identifying object segments, etc. But this is one example of getting the saliency map using subjective feedback. On the other hand, eye trackers are very powerful devices nowadays, and it provides us the gauge positions at regular interval in the image. So you can have gauge path. You can get the gauge path by this form, and the data would be in the form of an XY coordinate, that XY coordinate with respect to the image. So you can get the pixel points from there and with the corresponding timestamp. So through calibration you can always identify that which pixels are viewed by the viewers, and that is what ranges of XY coordinates compatible with display device resolution. So one typical example of eye tracking has been shown here. You can see that actually there are there are two gauge path, because one for left eye, another one is for right eye. Here it is shown left eye is blue actually, right eye is red. So this is right eye and this one is left eye. Okay, so you have this gauge tracking, the path you can get here. Usually, since it is plain, mostly you will find that the respective disparity is almost constant in this case, and it goes very nearby. So let us try to understand that how do you record these gauge points. So what is the technology? So let us also consider that factor. Then we will understand that how accurate is this kind of technique. So I will discuss one particular technique which is called pupil center cornea reflection technique, and to capture the two-dimensional gauge data. So there the concept is that in our eye the pupil is very easy to detect, because pupil has a very distinct contrast. Either it is very dark pupil or it is white, depends upon the illumination. So if you can illuminate, when you are imaging, usually pupil can be in these two forms, either dark pupil image or bright pupil image. But there is another interesting thing is that by a controlled illumination, suppose you have an IR LED, infrared LED, which does not have any effect on the viewer while viewing the image, but it records in the infrared sense, it would record the image of that reflection of that LED, that light source, and this reflection is called glint, and which is clearly identifiable because it's a bright spot. So if I can identify glint, position of glint, and if I can identify the position of pupil, using these two, we can identify the gauge location. That means at which point the viewer is looking. So this is what. So what we do here, that we capture this glint, which is the virtual image of the light source on convex cornea, and it is easily detectable as the bright spot. I mentioned that these are the pupil centers. So glint provides the reference fixed position of light source, because in the setup light source is fixed, and when you are looking at a particular object, with respect to that we consider, because light source is fixed, we assume that viewer is also it's stationary. So it has a fixed position. Only when the pupil moves, pupil will move, but with respect to the light source, pupil's direction will change or location will change. So pupil center position will vary depending on eye gauge location. So this is a thing. So what we measure in that case, if I identify the center of pupil and if I identify light source, so I can get this vector. I can get this vector which is called glint pupil vector. So we can calibrate this vector position. So these are the observations. With the vector has two components, and these positions are function of the respective gauge location in the image. And there are different models people can use. One of the models I will show for estimating the model coefficients of model. So this is a quadratic model. As you see, this is the x coordinate of the gauge location and y coordinate of the gauge locations, and they are function of these components of these vectors. These are the coefficients. So you can see that there are how many unknowns? There are 8 unknowns, and there are 2 equations. So at least you require 4 points to 4 measurements, I should say, to estimate these coefficients, 4 known measurements. So what you will find this kind of 2D eye gaze tracker, there is a calibration phase for every viewer. So viewer has to look at the screen And again, as a hand-eye coordination kind of thing, what I was talking about, here also viewer will be looking, will be asked to look at certain points whose coordinates are known to the system, and then by observing these glint pupil locations, by measuring these vectors, you can develop this regression, you can fit this regression model, and through which you can get the eye look and apply this model for further measurements. So, this is the principle behind recording two-dimensional gauge points. Now, let us understand that even there are 3D gauge eye tracker, which means it gives the respective three-dimensional positions with respect to a coordinate system definition. Usually, these are defined with respect to a viewer's coordinate system. We say it's an egocentric system. So, suppose viewer has an head mount camera, and which will from or a spectacle where the cameras are fixed and through which these are captured, or there are certain fixed two camera locations from where these eye gauge locations are captured. Now, let us try to understand what is meant by these three-dimensional gauge information. So, if I model our eye, a very simplistic model, that there are two circles. One is full, of course. This is the circle related to the eyeball, and this is a circle related to the cornea. And of course, there is a lens here, which is not shown here. There is a lens. We have the center of eyeball, and similarly, we have a center of cornea. And then given a target, this passes through the pupil. So, which means that your pupil is here, only this light is passing through the eyeball, other lights are not. So, and we consider that it passes because it is undeviated, it goes through straight. So, this ray goes undeviated and it hits the fovea. So, we have shown in the other directions is vector, just for the simplicity. So, this is the gauge point. So, this cornea and the pupil, so this is the pupil location, they define the three-dimensional gauge point. So, we need to measure the three-dimensional location of this cornea and three-dimensional location of the gauge point. Now, that we do by observing the images through a stereo camera. So, images of this of this target. So, this target will form some image here. So, we will observe the images and this one. So, this is a visual axis. So, say suppose this is the image that pupil forms here, and we observe this location, and we can get this point. On the other hand, if I have the LED, so use infrared stereo imaging to capture the pupil location, and 3D position of the pupil is obtained in this way, and then using the LED with a known location, you can also capture its corresponding image of the glint, that is virtual image of the glint. So, you can get the 3D position of the virtual image of the glint, because and which is the fixed reference position in the cornea. So, suppose you get this point again using this camera locations, you can get this point. This is a stereo camera, and so you get this point L prime, L1 prime, and you get also the location of the infrared LED. It is calibrated, its location. So, it defines a particular ray, and since it goes undeviated, it hits the center of the cornea. If I use another LED setup, so I will similarly get another image point L2 prime, and this will get this particular straight line, because if you know its reference L2, that will form another line. So, if I use the intersection of these two lines, they will give me the estimation of cornea. So, what I require this cornea, I require the position of the image of this target, which is giving me the pupil, and then that defines the visual axis or gauge. So, if I know this point, I will get the gauge information in this way. So this is how the three-dimensional direction of gauge is computed. So when we consider this kind of three-dimensional eye tracker, so as you understand that you get both two-dimensional gauge locations and also associated three-dimensional informations with respect to a world coordinate system from the viewers by referring to a viewer. So what we have sequence of 3D gauge location in an image itself. So where the viewer is looking, that also it can be given, and for a video with timestamp we could get it, and we also can get normalized 2D gauge location, that is to eye tracker in camera resolution, and then we get gaze direction vector and pupil centers of both eyes. These are certain information from 3D eye tracker, and even there are video eye tracker which performs at a higher rate at every frame these operations, and these are egocentric video. So there are now these 3D eye trackers, where head mounted 3D eye trackers, where you can mount the respective or wear a glass eye tracking device in the glass itself, and then you can get this kind of three-dimensional gaze information from the scene and the objects you are looking at in the scene itself. So there you get some more information like recorded video of the world scene itself. So you can record the video, and with respect to that video you can find out that which are the points in the frame are being looked at. And other than that, the motion of the viewer, that means accelerometer and gyroscopic values of head movements, those are also available, which is required for correcting the respective gauge or coordinate system, co-registering the coordinate systems. So one of the interesting thing of this data, because it also gives you various not only visual saliency, it now opens up several other opportunities to understand the cognitive processes, visual cognitive processes. Those are going through in our visual processing system, or in our brain, if I say. So eye movements, it is not automatic or reflexive action, and it represents the most frequent decision process carried out by the brain. So the conscious perception, it depends on the trajectory of fixated location. So we'll see that actually when we have this kind of gaze data, there are some of the different types of eye movements which characterizes particularly that nature of some of those points in that gauge locations, and that also shows how our perception mechanism works. Throws some idea, some insight on our perceptual processes, visual perceptual processes. So these three types of eye movements, those are observed. One is called fixation. So it occurs when the eye stops to collect visual data, which means it means actually fixations are those points where movements are less, and it stays, the gaze location stays momentarily for a few more than relative to other the gaze locations, they remain stable for certain time interval. Again, it can move, but that is the fixation. So around that point only the eye balls or eye locations are moving only. So this is so we call those things as fixated regions. Now there may be a sequence of fixated regions. So we'll see that. So this type of locations are called fixations, or movements are called fixations, and locations associated with fixations. Then there are saccades or saccadic movements. It moves the fovea rapidly from one point of interest to another point. So this is that transitions of the selective attention when we are saying. So it is saccadic movements are the movements for that selective attention. So you remember I discussed in that computational model that when you have the saliency map, after detecting the most salient zones, then you move to the next salient zones. So these salient zones are kind of zones of fixation, and saccadic movements are corroborating to that kind of model that this kind of transition takes place in the skids. And there are also microsaccads. When you have movement along the fixations. So even when you are fixating, then you have rapid movements around fixations. We call them microsaccads. So so this is a mechanism as where you may not remain stationary at a particular point. So our system has that kind of randomness, and our attention may not be so perfect and so controlled that it always remains at the same point. So this is a capability and capacity of of an individual, and more you do, like for if I consider the attention of an archer, and you understand that then that fixation has to be very accurate, it has to be stable. But when we consider a common person, no fixation is so stable. It has certain drift, and you drift and again you come back to that point. So those are microsaccads. So it serves as a corrective function. So these are some examples where it is showing the zones of fixation. So these red marks are zones of fixation, and these are saccadic movements. Microsaccads are not shown here. And there is also another interesting example. Suppose you have a text which reads like that: purists consider there to be only two true pizzas. Now this is a text, and it has been observed that if I use the eye tracker for a viewer to read this text, then we will see that these are the zones of fixation, right? So we give more attention to UR portion of purist, ON for considerations. This is there, this is only, and this is pizza. These are the fixated zones. On the other hand, these are the saccads. These are the saccads. This is the saccadic zones. So in scene viewing, fixations focus on visually salient parts with higher variability in saccads. So that is a kind of summarization, that is a kind of relations with respect to gauge data or gauge sequences and the salient region. So to understand more about this process, let us try to see that what are the characteristics of a fixation. It made up of multiple gauge points. So fixation is not a single point; it's a region. Around the region, your eyeball is moving. It is looking at different perspectives. It is just not looking at a particular point. It is looking at a region that we need to understand. And there, your gauge point is moving, scanning. Your gauge point is scanning within that region. But it's a small region, so it looks like it's a fixated region. Its duration is 50 to 600 milliseconds. So some points may take small time, and some may have more details. So that is interesting. Then usual duration is 100 to 300 milliseconds. So that is the usual duration. So you understand that all are more than 100 because when you are understanding something, when it is less than 100 millisecond, we just see everything is moving like video. And unless you keep the image momentarily stationary more than 100 millisecond, that won't make much impact on us. So when it is a video, the saliency is very different there. The motion has to be involved there. Then its angular velocity is 0 to 10 degree per second for system mounted eye tracker. So when we view, actually we consider the viewing angle is there. So this angular velocity around 50 to 80 degree per second for wearable eye trackers. And higher velocities compensate for head movements. So higher average fixation duration on a target, greater effort to sense or more engaging. So that is intuitively you can say that if you take more time in a fixated points, which means you are putting more effort to understand a scene for that, the description at that point. Let us now consider the cases of saccades and microsaccades. So, saccades, it triggered voluntarily or involuntarily, and duration of saccade, because it's a fast movement, it is 20 to 120 milliseconds, and usual duration is 20 to 40 milliseconds. You have to understand that saccade has a great role in selective attention, where microsaccades has a role in keeping you fixated. So, that microsaccade is something like feedback mechanism on correcting your fixated points. If you can drift away, and again you come back to the fixated point. But saccade is moving from one salient zone to the another salient zone. So, it's a selective visual attention, movement for selective visual attention. So, larger jumps produce longer durations. Naturally, this has been also hypothesized earlier, and now it has been observed experimentally. And microsaccades, the peak velocity is 90 to 200 degrees per second. So, it is very fast. Microsaccade is the fastest motion. So, some of the examples of movements are shown with respect to one particular image. So, you can see that this is the image which a viewer is viewing, and most of the fixation points are on the faces. See, these are the fixation points, and there are transitions from, there are other smaller fixation areas. So, it depends at how long you are remaining at a point. So, that gives you the strength of that fixation points, and how many times you are returning back to that point. So, these are all related. And then there are microsaccades. So, if I zoom this location, then you can see this is zoomed, and there are again small rapid movement around this zone. So, this is a microsaccades. These are the examples here. So, here just as I observed, that is also noted here, that human faces, they attract long duration fixations, and they are primary focus of microsaccades. So, through these red circles, these are shown here. So, this is one interesting statistics that I would like to share with you. Here, in our laboratory, we make these experiments and with an eye tracking device, and then by analyzing, we observe the velocities of these three zones, distribution of three states of saccades, fixation, and microsaccades. So, we found that these are the velocities. We have already mentioned those ranges, and these are the degrees per second. You can see that this is the fixation where the velocity is less. So, with degrees, and it is within, if I say on the average, it is around 5 to 6 degrees per second. No, 2 to 3 degrees per second. Whereas the saccadic movement, mostly the velocities would be around say 12, 13 degree per second. But microsaccades is of very higher velocity, and it has also wide range of variation. So, I should say it is around 40 degrees per second, 38, 39 at the peak, but it has a wide range of velocities. So, when we process the eye gauge data, because of some of the limitations of the devices, and there are various kind of noise which may be there, which is involved in computations. So, we may not always get the true samples or very correct, very noise, I should say reliable observations. So, some of the samples may not be very reliable. So, that is what is also obtained from these eye tracking devices, and some of the samples may be missing. So, you require some kind of post processing once you get the eye gauge data. So, you need to correction of practical sampling frequency. So, it is not equal to trackers designed one, and number of records in each second is not consistent. So, eye movement data synchronization creates difficulties in processing, and what we do that we actually take some quality data. So, if there is a quality in some eye trackers like Tobii eye trackers and the devices, the data they give, they also give you this particular measure of quality of the data, and you can use only the quality data there. So both left and right eyes are tracked, but they do not function equally. So in the case 1, the binocular data is used, and in the case 2, dominant or auxiliary eyes data is considered. So one of them is more used for understanding the visual scene. And if any eyes data is missing, it is set to blank or 0 for further processing. So this is what I was mentioning, that some of the processing things we do. Say we can fill in some of those small gaps, like gaps may caused by blinking of eyes. You can do some frequency correction, the number of times it is being there. Linear or spline interpolation typically used. So when it is missing, because there is a trajectory, so you can use interpolations of the data what is available and interpolate the data what is missing. And for data filtering, so you can have high sampling frequency for better tracking, but since there would be noise. So what we do, that even if you take eye gauge movement for higher sampling rate, you bring it down to lower sampling rate. You can smoothen it by moving averages or moving median methods and take the data from there. So identification of fixation, saccadic and microsaccadic intervals, that is one of the major tasks of this kind of eye gauge analysis. One cue I have already mentioned, that I told you that velocity profile give you some indications, but it is not a very hard decision, because they vary with certain ranges and there are overlapping ranges. So one has to consider the behavior of the trajectory. If it is a fixation, it should be concentrated on a small zone in the image. If it is saccade, it should be long jumps from one point to the another point. Not only the velocity first, it should be. If it is microsaccade, then the velocity is also high and it would be around the fixation points. So all those characteristics by definition should be exploited to identify those zones. So some of these things has been mentioned here, like angular velocity to identify fixation, saccades and microsaccades. This is one of the major cues. Our distribution or spatial proximity characteristics of cluster, as I was mentioning, that the cluster and its respective spread over the space, that is important to understand. Then long enough duration to identify fixation points, and fixations marked based on duration and velocity. Sometimes very close fixations, they need to be marked to a larger regions. So there are several uses of process data. So process gauge data obtained, it reflects the observer's interest or gauge target. So this is one of the major applications, that how do you decide, or how do you say that what is the interest of the observer. So the behavior. So one of the objective of eye gauge analysis is to study the behavior of an observer. So it is quite often is being used, increasingly it is being used for by the psychologists or psychiatrists to understand the behavior of their subjects. So let me provide you some of the applications in this case. Like in the computer science applications, you have attentive user interfaces. So eye contact as attentional cue to engage users in a more sociable process of turn taking. Say eye contact sensor turns on a light. So some kind of user interface you can think that by recording your eye movement, your environment understands your intention and then performs that action. It can be used for a collaborative systems, because the eye gauge is also a mode of communications. So it aids multi-party mediated communications. You can use it for screen pointers. So without using hand, through your movement of eye, you can develop this kind of GUIs. Cognitive modeling is one of the major applications where it can predict, it can develop the better model for accuracy and ease of learning. So eye-mouse movement relationships is there. So neuroscience and psychology, I just mentioned earlier. So for scene perception to develop a set of tasks to uniquely locate interaction of the context with object. So, fixations, it can give scene, gest and rest to field detail.